Hi everyone. This week we're going to talk about acids and bases, and we're going to start with talking about just their properties, some nomenclature, and some theories related to acids and bases in this first video. So first and foremost, acids and bases are something that you should be familiar with. Some of the common things that we know to be acidic are your stomach, batteries, battery acid, vinegar, sodas, and then some of the things we know to be basic are ammonia, soaps, things like Drano and an antacid, which you use if your stomach is overly acidic. It'll calm your stomach down. And typically speaking, when we have a reaction between an acid and a base, we call this a neutralization reaction. General properties of our acids: they have a sour taste to them, so your Sour Patch Kids candy. They are corrosive, meaning that they eat away at substances. They sting open wounds. They look like water usually. You have a solution that's acidic and it does look like water, as many of our chemicals do. They'll turn your litmus paper red. They are electrolytes in solution, and remember, this means that they can conduct an electrical current. They tend to react with metals to form hydrogen gas. Their pH is less than 7, and they'll react with bases to form some salt and water. Strong versus weak acids, we're talking about the strength of an acid depending on how much it dissociates in solution. If you remember what dissociates means, it means that it breaks apart into its ions when you put it into a solution. So if I had, for example, hydrochloric acid, HCl, it will fully dissociate into H plus and Cl minus when it's in solution. And because it fully dissociates, it's considered to be a strong acid. There are 6 strong acids that you need to know. They're listed down at the bottom here. So I have HCl, HBr, HI, HNO3, HClO4, and H2SO4. You should know the names of most of these, if not all of these. And we're going to get into the naming system for the first 3 there, which are the ones that are probably unfamiliar to you. If it's not a strong acid, it means it only partially dissociates in solution, so it will not completely separate all of those species. For our naming system, in a binary acid, binary meaning I have hydrogen bonded to some other element, usually it's a halide, one of your halogens, or something else that's very electronegative, it will not contain an oxygen. We would name it as hydro something ic acid, and that something comes from the base of whatever it is that it's bonding to. So for example, if I was bonding H to Cl, it's chlorine, so it's going to be hydrochloric acid. HBr, hydrobromic acid. So it's based off of the element that it is bonding to. If it is an oxyacid, meaning it does have some oxygen-containing polyatomic ion that it's bonding to. So if it's hydrogen plus a polyatomic ion that does contain oxygen, we do not use that hydro prefix, and instead we'll change the AT ending to IC in the acid name, or if it's an ITE ending, we change it to OUS in the acid name. So for example, I have H2SO4, SO4 being sulfate, so 8 to ic, that's sulfuric acid. HNO3, NO3 being nitrate, 8 to ic again, it's going to be nitric acid. HNO2, that's nitrite, ITE ending. That's going to change to the us acid, so it's nitrous acid. So that's your naming system for when you're talking about acids. We're going to flip over to bases for a second. So bases are properties. These taste bitter as opposed to acid sour, so anything with that bitter taste to it. They are caustic, which means they burn organic tissue. They're very slippery, so things like your soaps. And again, they often look like water. Many of these solutions look like water. They'll turn litmus paper blue. They are also electrolytes. They typically do not react with metals. Their pH is greater than 7. And our hydroxides of group 1 are all strong bases. So anything that's in your group 1 of the periodic table, meaning your lithium, your sodium, potassium, so on and so forth, going down, bonded to hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide, so on and so forth, are all considered to be strong bases. And calcium, strontium, and barium as well from that second group. These will also react with acids, producing salt and water. And when I say salt, I do not mean salt like your table salt. I mean salt in the chemical sense, meaning I have a metal and a non-metal bonded together. So it's a chemistry, salt, and water. For naming our bases, you already know how to do these. They're named according to our ionic nomenclature, where I name the first compound just as it is on the periodic table. And in this case, it's Na, which is sodium. And then the second one changes to an IDE ending if it's just something off the periodic table. But in this case, we're talking about hydroxide, which is a polyatomic ion, so it keeps its name entirely. So this is just sodium hydroxide. If I had something else like KOH, it's potassium hydroxide. So it's the exact same nomenclature that you are used to. The theories on acids and bases, there are a couple of perspectives we're going to go over. There's the Arrhenius theory, the Lewis theory, and the Bronsted-Lowry theory, and that's the one we're going to focus on the most. But I do want to introduce you to each of the others first, where the Arrhenius theory is talking about a compound that increases the concentration of H plus specifically in aqueous solution. So if it's an acid, it has to have H plus ions in the solution. H plus does not freely exist in water. Typically speaking, our H plus reacts with H2O and forms H3O plus. And this H3O plus is called the hydronium ion, hydronium. When hydrogen forms an ion, it is essentially just a proton. And we'll talk about that a little bit more in a second. So with this theory, a base is something that increases the hydroxide ion concentration within an aqueous solution. What this means is that a base would have to have an OH in order for it to be considered a base for the Arrhenius theory. However, there are some problems with this. This theory, first of all, means that all acids have to have an H plus and all bases have to have an OH minus, and we know that this isn't true. By this definition, things that we know to be bases, like our NH3, which is a Lewis base, or an acid like BF3, which is considered a Lewis acid, would not be classified as either an acid or a base. So going forward, Lewis acids and bases, we have an electron pair acceptor, while the base is the electron pair donor. And it results in a coordinate covalent bond. And if you remember what this is back from way back when we were doing our Lewis dot structures, a coordinate covalent bond is what happens when you have two atoms that are bonding together and one of them is supplying both of the electrons used in that bond. Typically, you'd have each sharing one electron, but in some cases, one atom shares both electrons in order for the bond to form. That is a coordinate covalent bond. So in this case, if you look at the picture down at the bottom here, we have our Lewis acid that is reacting right here, Lewis acid, with the Lewis base. And the Lewis base in this case is going to have both of those electrons supplied to the bond that's about to form, which means this is a coordinate covalent bond. So this pair of electrons will be shared with that boron there, and we end up with our final product. So this one is talking about our electron pairs being transferred, and the acceptance versus the donor is determining whether something's an acid or a base. So this is a bit more broad. It doesn't confine us to having to have that H plus and OH in order to have an acid or a base. The Bronsted-Lowry theory is an extension of this in the Arrhenius theory. We're talking about a proton donor and a proton acceptor. So in this theory, an acid is a proton donor. So it's giving up one of its H pluses. And the H plus, if you look at the picture on the right here, when I have just regular hydrogen, it has one proton and one electron. H plus means it lost its electron, which means it's just a proton now. So it lost the electron, it has one proton. So H plus is essentially a proton. So when we're talking about something being a proton donor or a proton acceptor, we mean a hydrogen that's lost its electron. So it's accepting or donating that hydrogen atom that is just a proton. So in this theory, what happens is the acid gives its proton to the base. So in this scenario, we can look and see that my HCl loses its proton. On the right-hand side, it's just Cl minus. That makes this the proton donor, so this would be the acid. And my NH3 becomes NH4, making it the acceptor. So this would be the base by this definition. So in this reaction, our protons are transferred from one to the other. These reactions are reversible, and we'll talk about what determines which direction that reaction will flow in a second. But this is consisting of two species, and one is an acid, one is a base, and that differs by just the loss or gain of that proton. The conjugate base is the name of the species after it has given up a proton. And then the conjugate acid is after it has accepted a proton. So on the left-hand side, we already identified our acid and our base on the previous slide. So I have my acid here and my base here. Now the conjugate acid and conjugate base are on the right-hand side, or the opposite side of the equation. And the conjugate base is what the species looks like after it has given up a proton. So my HCl over here gave up that proton and became Cl minus, making this the conjugate base. My NH4 plus is what happened after the base accepted a proton. So this would be a conjugate acid-base pair, and this would be a conjugate acid-base pair. If we're identifying our acid-base pairs and showing proton flow, which is something you will have to do in your homework, what you're going to do is you're going to identify what direction the proton is being transferred, And then following exactly the rules we just named above and that are written underneath here, you identify the acid and base, acid being the one that's giving away the proton. And if you look, the conjugate acid is still the one giving away the proton in this example. So you're always naming the one that's giving away the proton, whether the reaction is proceeding forward or in reverse, as the acid. Conjugate acid is what the base becomes after gaining a proton. So if we're writing that formula, if I just gave you the formula of some base and I wanted you to write the conjugate acid, you would add hydrogen to that base's formula and also add 1 to the charge. So seeing how that works here, if I have the base being my H2O right here, I would add hydrogen to that. So H2 should become H3, and I'm also adding 1 to the charge. So it should be H3O plus. And if you look at the right side, H3O plus is what it produces. So that's going to be the base conjugate acid pair. Then on the opposite side, if I'm trying to figure out from an acid what the conjugate base is, the acid would lose a hydrogen and lose 1 charge. So I know this is my acid, my HCl, and it's going to lose 1 hydrogen. So that hydrogen goes away. It's just chlorine now. And it also loses 1 charge. So it's going to be Cl1 minus. And on the right-hand side, you can see that is what forms over here. So I have that as my acid conjugate base pair. So those are your 2 pairs. And that's something you will have to do with in your homework. Here's another example for you, just so that you can get familiar with this, and then we'll do a couple more. So I have on the left and right-hand side here my equations labeled out, where my NH3 is my base, because if I look at the equation, my H2O on the right-hand side becomes OH, meaning it lost the hydrogen. So the hydrogen is being transferred this way. The thing giving up the proton is your acid. So that's my acid. The base is the thing accepting the proton, where NH3 becomes NH4. It clearly accepted a proton, so that makes that my base. Opposite direction here, if I were to push this reaction backwards, my NH4 would have to give a hydrogen to my OH minus, in which case it would become H2O. So NH4 would be the proton donor on the right-hand side of this equation, making it the conjugate acid, because the acid's always the one giving up that proton, versus the OH, which is the one accepting the proton in the reverse reaction, and that makes that one the conjugate base. So that's your acid-base pairs for this particular one. There's a term down at the bottom of this slide here that says water is amphoteric. So if you look at this side says that our H2O is our acid. This one had H2O labeled as a base. The word amphoteric means that water can act as either an acid or a base. It's able to become either, depending on what it is that it's reacting with. So it will perform as either in any given scenario. We know that HCl is a strong acid. That's one of the ones in the list, the 6 that you had to remember. So how strong would its conjugate base be? If you're asked to figure out the strength of something, the general rule is the stronger an acid is, or a stronger a base is, the weaker its conjugate will be. So if I have a very strong acid, it will have a very weak conjugate base. If I have a very strong base, it will have a very weak conjugate acid. If HCl is a strong acid, Cl- must be a very weak conjugate base. The reasoning behind this is that HCl can only be a good proton donor if that chlorine ion is a poor proton acceptor in the first place, so it doesn't hold on to it very tightly in the first place, and thus it must be a weak base. Here's a couple more examples that we'll walk through really quickly here. So looking at the left and right hand side of the equation, I can see that my CO3 2- gains a hydrogen on the right hand side, whereas my H2O loses a hydrogen. That means that this H2O must be donating a proton. To show my proton transfer there, I'm going to go ahead and write H plus above it. So that's how you show your proton transfer. And then that would mean that the donor is going to be the acid, whereas the acceptor is the base. Then going on the right-hand side, if we were doing this reaction in reverse, my HCO3 would have to donate that hydrogen, that proton, to the OH minus to reform that water. Since that's the donor, this is going to be the conjugate acid, which makes the other one the conjugate base. Taking a look at the second one here, on the left-hand side, I can see that I have HNO2, whereas on the right-hand side, I only have NO2. So this one's losing a hydrogen. That hydrogen is being donated in this direction to the left. Versus on the right-hand side, I have my NO2 that would need to gain a hydrogen to go back. So I would need to gain a hydrogen. So my hydrogen would be transferred in this direction. So you can label your protons like so. And then the one that's giving up the proton is always going to be the acid. So on the left-hand side, my HNO2 is the acid. which leaves this as my base. And on the right-hand side, this would be my conjugate acid, whereas this would be my conjugate base. So the first part of your homework is going to ask you to do this, where you're going to label an equation with the acid base, conjugate base, and then showing that proton flow. That's exactly how you would do this. So now we alluded to this earlier. We know that these reactions are reversible. So how do we know which of these reactions is the one that's actually going to take place, the forward or the reverse reaction? Weak acids and bases have less energy than strong acids and bases. And we know that equilibrium will favor the side with the lowest energy. Everything tends towards the lowest energy. So in this case, our acid-base reaction is going to proceed to the side that has the weakest acids and bases. How do you tell which is the weak acids and base? Well, you know your strong acids and bases, so you know the conjugate pairs that will be weak as a result of this. So for example, here, we know NaOH must be a strong base. It's one of the ones from our list for the bases. So its conjugate acid must be really weak. That means the equilibrium is going to lie to the right side where that weak conjugate acid is. Another thing you can look at is these pKa values, and we'll not get into calculating this. You'll do that when you get to AP. When you look at the pKa values, the equilibrium lies in the direction that has the higher number. Low pKa values indicate a very strong acid or base, so the higher pKa values means it's weaker. So you'd look at those values, the side that has the higher pKa is going to be the side where the equilibrium lies towards. So this reaction would shift to the right. A couple different types of acids when we're naming our acids here. There's monoprotic and polyprotic. Monoprotic meaning it's an acid that only donates one proton per molecule. Protic meaning proton, mono meaning one. So HCl has one proton to donate, HNO3 has one proton to donate. Polyprotic means it can donate more than one, and there are specific names. So you have diprotic that can donate 2, triprotic that can donate 3. So here, when we're looking at a polyprotic acid, your polyprotic ionization, so the way that your acid will dissociate into solution, occurs in 2 stages. It will give up that first proton, and it will form the H3O+. In this scenario, my H2SO4 gave up the first proton, and it became H3O+ and HSO4-. That HSO4- still has one proton to give up, so it will then react with additional water, and you end up with another H3O+, and then SO4-2-, in which case it doesn't have any more protons to give, and so that ionization process is complete. One thing you should note that's a common misconception here is that more hydrogens does not mean an acid is stronger. You know the strong acid. Just because it has more does not mean that it is a strong acid. The autoionization of water refers to the fact that water will, even pure water, automatically ionize into H3O+ and OH- in small amounts. So the word amphoteric, we talked about, it means a species that can react as either an acid or a base, which water can do. It reacts with itself to be an acid or a base, depending on which way you want to show that direction of transfer. And we end up with our H3O+ and our OH-, in which case the H3O+ is that conjugate acid and the OH- is the conjugate base. There's another term for this when we're talking specifically about a Bronsted-Lowry acid base pair. So something in Bronsted-Lowry that can do this is called an amphiprotic acid or base, meaning it can gain or lose a proton. So the summary of this theory is that a base has to accept protons, whereas OH- would only be one example of a base in this theory, which makes it much more broad and it helps us to incorporate more bases. Acids and bases can be ions as well as molecular structures in this scenario because we're just talking about that donation of that proton. Acids and base reactions are not restricted to just aqueous solutions under this theory, and some species can act as acids or bases depending on what they are reacting with. So the reason that we use this theory so often is because it is much more broad and encompasses more things than any of the previous 2 theories. All right, guys, now that's it. You have a worksheet on Schoology. You're going to answer some questions on topics that were addressed in this video, so go ahead, give that a shot. There's also some questions at the end related to acid rain. You'll have to do a little bit of research to answer those questions, and there are some links provided at the top of that portion of the worksheet, so go ahead and use those. And that's it. Once you finish that, and once you finish your survey for the end of the year, you guys are done. Congratulations.